awkward? Okay. So the real numbers, week number 1. So we're going to be reviewing the basic properties of the real numbers, and then we're going to be looking at algebraic manipulation, skills and fundamentals, inequalities, and absolute values. So one of the most important properties of the real numbers are integers. So that we know that the integers have basically numbers such as 1, 2, 3, and we also have negative integers too, like -1, -2, -3, and so on. With 0 in the middle. So like these integers, they are basically denoted by the Z. And it has a bar, 2 bars in the middle, like slanted like that. So examples, we can do adding, subtracting, multiplying of 2 integers yields another integer. For example, 3 plus 4 equals 7, 8 minus 2 equals 6, and 6 times, let's say 5, equals 30. However, the quotient of 2 integers is not always an integer. And so this means that we can divide an integer by another integer. So examples like 8 divided by 2 equals 4. And this, of course, is an integer. But it's not always. So 8 divided by 3 is equal to approximately like 2.66 ... Of course, this number is not an integer. Int. Okay, so there are things called rational numbers. We were looking at integers, now we're looking at rational numbers. A rational number is a number that can be written of the form m over n, where m and n are integers, and the denominator, which is n, the number on the bottom, is not equal to 0. So division by 0 is not allowed. So we can denote the set of rational numbers by this thing called Q, like that. So this is what we denote it by. And there's examples, right? So examples. 8 over 3 is a rational number. As you see, 8 over 3 is an element of the rational numbers. We just said it was equal to 2.666. So this symbol here means is an element of and we see the numerator is the 8 and the denominator is the 3, just to be clear. But note that 8 is an element of the integers, and so is 3. And 3 is also an element of the integers. So another example would be like 6/2, where we have 6 is the numerator, and the 2 is the denominator. So 6/2 is a rational number. I'll just use the number sign. Also, it's equal to 3, which is an integer. So with like these rational numbers, there's addition, subtraction, multiplication, and even division of two rational numbers, except for when the denominator is 0, always yields a new rational number. So this new rational number here. So this means if x and y are an element of our rational numbers, then so x plus y, so we can add them. It's also going to be a rational number. We can subtract rational numbers, and we also get a rational number. We can multiply them. This is the multiplication symbol. And it's rational numbers, and we can divide. There's symbols for this. So rational numbers. This is if, of course, if y does not equal to 0, of course. You can't, if you try on your calculator to divide by 0, you're going to have a problem, right? So you can't divide by 0. So there are infinitely many integers. How do I prove that to you? Like we could say it, but like what would the proof kind of look like? Well, if I say, like if someone says a number, someone else could say another number. Someone could say 9, and then another student could say 20, and then a student could say 21, and another person could say 1,000,000, and then 1,000,001, and a trillion, right? And we could just keep going and going and going. So there are infinitely many integers, which we kind of understand this. So we could kind of draw it on a number line with 0 here. Let's say 1, 2, 3, -1, -2, -3, ... So these set of integers, let's use a different color. There are infinitely also many rational numbers too. Infinitely many rational numbers. In fact, there are infinitely many rational numbers between any two integers. So between like 0 and 1, there's a half. That's a rational number. Between 0 and a half, there'd be 1/4. And then between that, 1/8, etc. So why is this the case, kind of? Well, you could average, what am I just doing there? Kind of showing you that I'm taking 0 and a half, and I'm averaging, and I'm getting 1/4. And then I'm taking 1/4 and 0, averaging those two numbers and getting 1/8. So there's all these, so this is kind of like I'm waving my hand, but this is the proof. Same over here. So there's a whole bunch of rational numbers. I'm just gonna put them in purple. So and there are also numbers. So let's go back. So we have the integers, and we know the whole real the line also is the real number line, R. So that's all the numbers, because our topic here is the real numbers. So I'm talking about all the numbers. Now between the integers and the rational numbers, there's this thing called the irrational numbers. What color would we like? Let's go with black. So there's also these other numbers in here. So you can imagine the integers, all these numbers. So there are numbers that are not actually rational. And I'll write a little statement down here. Did the person need help? Or... Thanks. Maybe we should open the door to air out ventilation due to, maybe it'll be safer for us. So there are infinitely many rational numbers between, let's say, 2/3 and 12/13. And you can prove this again by like just averaging between the two numbers. So now there's these numbers that are not rational. And there's an interesting proof actually in this textbook in chapter 0, showing how the square root of 2 is not a rational number. It's a little bit like, so I wouldn't even really say it's beyond the scope of this course, but it's a little time consuming, and it's in the textbook so you can read it. And actually it was the first proof that I ever kind of saw at university. So I do advise you to kind of read it. So you can't write this over m/m though, right? So you see why it's irrational, right? Number. So this is going to be a rational number, square root of 3, pi. These numbers cannot be expressed as the ratio of two integers. Therefore, they are not rational numbers. So the real numbers, since the set of rational numbers don't cover all the numbers, we know we need a richer number system, and that is the real numbers. So the real numbers are things like, of course, an integer, -7, 5/7 is a rational number, square root of 2, square root of 3. These are all the considered the real numbers. So that's what I said back here. This red R is all the real numbers, rational plus irrational. So a real number that is not rational is called irrational. So the fact pi, square root of 2, square root of 3 are irrational numbers. So they're irrational. And we can do things like addition, subtraction, multiplication, and even division of two real numbers. As long as the denominator is not 0, it always yields a new real number. So we can draw a set of, try to explain this with a Venn diagram. So we can draw a picture. And in here, you have, let's say, the set of, like, you have 0, you have -2, 7. These are the set of integers, all in here. Outside, in this other box, you have things like 2/5, 9/2, and let's say -11/4. And these are rational numbers. But an integer is also, why did I draw the circle inside the rational numbers? Well, an integer is a rational number. Like 7/1 is also rational. So it's in the set of those numbers. I'll go back to blue. And then over here, we have the set of irrational numbers, things like square root of 2, square root of 3, and pi. So this is the set of irrational numbers. And this whole thing is, of course, the set of real numbers, which is denoted by R, the whole thing. So I'll make that little point over here. Note that any integer is also a rational number. For example, seven is in a set of integers, and it can be written as 7/1 is also rational. So let's apply our basic knowledge of these number sets to show that a given number is irrational. We already sort of discussed that the square root of 2 is an irrational number. Why did I? Let's go back. Because you can't really express it as the ratio of two integers, square root of 2. How would you do that? So we know for a fact that it's an irrational number. Like this is a fact. I use this fact to show that 5 times the square root of 2, and the rest of these are also irrational numbers. So we want to show this. Show this as irrational. So I did write it. So we can rewrite the square root of 2 is equal to 5. So we're rewriting what the square root of 2 is. So it's equal to 5 times square root of 2 divided by 5. We'll all agree that the left-hand side is equal to the right-hand side, correct? And now we're going to imagine that 5 times the square root of 2 were rational. So we suppose the opposite. Then we would see that 5 times the square root over 5 would be the quotient of two rational numbers, the top and the bottom, which must be rational number. But this isn't, it's equal to the square root of 2, which is already known as irrational. So we get a contradiction. I'm going to try to write it out a little bit better here. So let me explain. So let's write it. So 2 is written as 5. So we can write it this way. And we agree that the left-hand side is the right-hand side. And this is known to be irrational. Correct. But we're trying to prove that 5 times the square root of 2 were irrational. So we're supposing or saying if this were rational, what happens? And we know the bottom here, the denominator, it's an integer. So it's also a rational number. So we're using, I'll write this out, the quotient of two rational numbers, because we have a rational, so we're supposing the top is rational. So the quotient of two rational numbers must be a rational number. Because we said that before. That's one of the things we earlier said. But we know that it's irrational. It's equal to this. If this were rational and this were rational, then it should be equal to a rational number. But it's not, because this is irrational. So therefore, the conclusion, so this is like contradiction. This is proof by contradiction. So the conclusion it was false. To assume that 5 times square root of 2 is rational. So we conclude five times 2 square root of 2 is irrational. So let's do this one. Show that a square root of 2 plus an integer is irrational. It's kind of common sense, but because we have a rational number plus an integer, so it's still going to be irrational. But how do we kind of explain it? So note that the square root of 2, we can rewrite it, and it's the same thing, is equal to square root of 2 plus 7 minus 7. And we know this part, square root of 2, is known to be irrational. If you're really curious, again, it's in chapter 0 in your textbook, the proof. And we're supposing this part here, if this were rational. And we have this, of course, 7 is, of course, an integer. So it's also a rational number. So we suppose this were rational, we're trying to show that it's irrational. So if the square root of 2 plus 7 were rational, then this whole thing, square root of 2 plus 7 minus 7, which is obviously all equal to the square root of 2, should be rational. Why? Because it's the difference of two rational numbers. Because if this were rational, and this is obviously is rational, then the difference of two rational numbers, which I earlier said is a rational number. But we know it's equal to an irrational number. But so this is not rational. So therefore, the conclusion is, of course, the square root of 2 plus 7 cannot be rational. So then it's irrational. Okay. This question I'll leave for you to do as an exercise. So the real numbers is useful for representing and comparing real numbers. So again, we have, like, let's say the real number line. We have positives over here, negatives over there. And we can take two numbers like X and Y. And we see that if X is on the left, of Y on the real number line, then X is less than Y. We know this, but so this just means, like, if we draw a picture that, like, let's say we have 3 is X and Y is 4, then pi, and we know that pi is between the two numbers. So it's just about drawing the number line. Yeah. And then there's operations of addition and multiplication are commutative and associative of the real numbers. So let's see the properties. So in terms of addition, we can do X plus Y is equal to, of course, Y plus X for all X and Y in the set of real numbers. Sorry, for all X and Y in R. And we can also do multiplication. So X times Y is equal to Y times X. This means, of course, times for all X, Y in R. Then there's associative properties. So we can do X plus Y plus Z is equal to, of course, X, plus Y plus Z, and put the brackets that way. And X times Y times Z is, of course, equal to X times Y times Z. So these properties all hold for all X and Y in R. What about down here, the little question? What about subtraction and division? Are they commutative and associative? Anyone? Anyone?
Well, would they not be that minus y is not equal y minus x?
Right, yeah, exactly. And same with the division. So usually those properties do not hold. So I'll make a little note down here. Commutative and associative properties sorry about my handwriting. Don't usually hold for subtraction and division. And what he did was right. Like he thought of a counter example. So let's think of one, like, for example, like 7 minus 3 is equal to 4, but 3 minus 7 is equal to -4. So these numbers, 4 and -4, don't equal each other. Can you read that? Is it clear? It's a little messy. Can you? I think it's hard writing on an angle like with this thing. Okay, so there's the order of algebraic operations. Expressions inside parentheses should be calculated before further computation. This is BEDMAS essentially. So an expression with parentheses inside the parenthesis, evaluate the innermost bracket essentially first, and then you work outwards. And then, so let's look at this. So here we would calculate, what is the first thing you do? How to calculate this? 8 minus 2, right? And you get 6. Then we use, then it's multiplied by 3 essentially. Plus 7 minus 5. So then we do 6 times 3. So 6 times 3, which is 18, plus the 7 times the -5. So 18 plus 7 is 25. Yeah. So then we do this, which is 25. So we have 25 times -5. And then we multiply it together. We get -125. Point is that like you start inside the bracket and you work out. So let's just evaluate this one together. Feel free to speak. So where do we start? Yeah, so 7 minus 4 is 3. So we do this part. So then we have 12 minus 3 times this part. 3, and then we can multiply 8 times 5, which is 40, right? Now we do these brackets individually. What do we get? Right, minus 37 times 12 minus 3, which is 9. And then our final answer is anyone else? I got something else. Yeah, minus 3, 3, 3. Oh. Okay, so I think that's about it. I'm at my time limit. So I'll do these next class, which is fair. Yeah. I'll have another sheet and I'll put it online. Thank you. One second.